So our next speaker is Fernanda Duarte. The presentation will show up. So actually we're going back to Oxford now, where she's sitting since a few years after we met during her postdoc in Uppsala with Lynn Kammerlin, but then she's been there in Oxford for a number of years now. She was not in the last meeting, but a lot of her students were presenting. I think that your students were bringing them large number of posters. So we are very looking forward to your talk about transfer learning and heterocycle synthesis prediction.
Thank you very much. Good morning, everyone. And thanks, Hugo, for the introduction and invitation today. It's a great pleasure to, see you go again, always, and be back learning about free energy perturbation method and many things that I learned back in Uppsala from Hugo, Johan, and Lynn at that time. But I'm coming from a very chemistry point of view. Sorry, is this a pointer? And today I will be probably bringing you back to thinking about the molecules that you're doing the calculations on and thinking what else we can do in that area. And just to introduce what we do, we are very much interested, as many of you, thinking how we can contribute with our very basic knowledge to help in this process, going into exploring molecules that will be good inhibitors, good active molecules in different ways. And that is a big goal that everyone has. And actually, there are many different approaches. People can do synthesis, computation, AI. And from us has been very much in this niche area that we are very much organic chemists interested in using computation to facilitate that effort. And that is the work that my group has been doing, focusing very much into understanding chemical reactivity. With that, we design new molecules. We go from very small molecules in solution to larger systems in supramolecular system to explore solvent effects and environment to larger enzyme catalytic processes that we want to model, very much always comparing to the background reactivity. How can those systems modify and fine-tune the reactivity of those molecules? And very recent work that we have been doing has been connecting these different areas, which I found amazing, and is something that we have been able to do in Oxford, joined by excellent scientists like Ed Anderson in the synthesis side and Paul Brennan in medicinal chemistry. And in this work, for example, we're looking at this very tiny, very crazy molecule that is very popular these days, and how we can improve the synthesis ability and the reactivity of those to generate new scaffolds. So doing very fundamental work at the physical organic chemistry level, we have been able to identify synthetic routes that allow us to define new scaffold, now functionalized systems that we can move forward into replacing those scaffolds in drug-like molecules. And that is very interesting because we really want to modify the aromatic rings that we have now currently available. We want to generate more sp3 molecules, but also different heterocyclic compounds there. So we have been exploring those things, and very interestingly, Paul has been able to test those systems in the lab, ensuring the chemical properties remain the same, but actually lipophilicity and other physical chemical properties can improve when we introduce those different functionalized systems. And alongside, we have been also developing tools, and there has been always been more a need for the science that we want to do more than a motivation by itself. So developing tools to automate the reaction pathway search, for example, when we want to identify new synthetic routes, and also how we want to identify new catalytic cages, or just do simple machine learning models that we can do, just small data sets that we have, and how we can train models very easily for the chemistry that we want to do. More recently, in collaboration with Daniel Collan and Julien Michel, we have been also been interested in introducing machine learning potentials to improve free energy perturbations there. But from that introduction, I would really like to move today to maybe something that is less free energy, but more chemistry related. And it's how we can enhance the chemical space of the molecules, drug-like molecules that we want to synthesize. As I mentioned before, sp3 compounds are very promising, and we're exploring different ways to do synthesis and to explore new scaffolds there. But also heterocyclic compounds have a special place in medicinal chemistry. And our interest initially, this was a few years ago when Eva joined the groups. She's an excellent PhD student, just now finishing. She was joined by a master's student, Josh, and we were collaborating with people in Exantia and with Paul Brennan, thinking how we can use computational chemistry to expand the chemical space, to discover new synthetic accessible heterocyclic compounds. And our naive idea at that time was very much on our approach of mechanistic analysis, so we'll identify synthetic approaches and calculate the mechanisms to obtain them. Very kind of a standard system, maybe with some graph representation and initially thinking about machine learning, but this was 4 years ago and we're not planning much. But actually Eva took the project way far and decided to choose a different approach. So before telling you what we have been doing here is just to convince you, for those of you that are not much medicinal chemists, that heterocyclic compounds are very important. If you think about the most popular drug-like molecules, you will always identify an heterocyclic compound there. Very important for permeability and to keep to make the drug available actually into the body. And also if you look at natural product compounds, you can see that they are present in a large range of them. And as always, we want to mimic what nature has been doing to identify new drugs. And this is just an example of how an heterocyclic compound can substantially improve properties of the system. So in this case, we have an inhibitor, and just by changing one of the carbon atoms, you can increase the binding in my case, or not. You can leave something that is, in this case, inactive to something that can be substantially improved. They can also collate metals, how to modulate polarity, and so on. So a lot of fine-tuning can be done with just modifying the place of where nitrogen and oxygen can be located. But as we know, that is not very easy. And those genetic models tend to tell us, oh, these are the molecules that we want to synthesize, but they say, oh yeah, the chemists will do that. And actually, as chemists, that is very difficult to do. There was a few years ago, 2009, this paper, the vehicle data set, that suggested all the potential heterocyclic compounds that could be synthesized. So let's go crazy, think about the 5 and 6 memory that we can obtain. Most of them, according to very basic chemistry rule, were considered to be not accessible. But actually, there was a range of them, as a small amount, but I think more than 3,000 heterocyclic compounds that were out there. Potentially could be obtained if we chemists will try to synthesize them. And actually, since then, there have been only a handful of them being obtained. So what is going on? What is happening there? And that was a question that we wanted to address. But Eva decided to take a different approach to think about how to obtain them, rather than thinking, okay, we want these compounds, and we will calculate the mechanism for them. Let's do retrosynthesis. And this is something that we chemists do all the time. And the rationale behind that always is sold as something beautiful, very exciting, rewarding, but actually for a synthetic chemist, a very painful process, okay? And the process is, each step is a single-step synthesis that you have to plan. In order to break down your molecule is simple starting materials, hopefully very cheap and green starting materials. And we are just newcomers to the field that have been exciting and very amazing work in this area, starting from the work of Core 8 in the 60s, and many people that have been developing different tools to teach chemistry to computers. And a few examples that we have been considered very relevant for the work that we wanted to do was thinking about template-based approaches. This has been the most common approach until very recently, where you will put rules into the computer, maybe manually putting rules, or maybe defining some templates that you hard-code into the system. So when the computer sees a new molecule, can identify something similar for this template library. And most of these approaches work in that way. There is, for example, the ring breaking approach from AstraZeneca that work in this approach. You consider this molecule and identify the mapping that can identify the ring closing that is taking place there. But a few years ago, there was this amazing work coming from IBM using natural language processing, in particular the transformer architecture, to treat chemistry as a language, a translation process. How we can translate reactant into products, or the other way around, products into reactant, just like retrosynthesis will do. So we decided to explore those two approaches, template-based and the transformer approach for the chemistry that we wanted to do. Initially thinking that that will be just a step in our workflow to obtain the synthesis that we wanted to try. But actually the models that we started to train, just in a few data sets, we identified that in many cases there was they were not solved. And we tried, this is just one example of data set, but we tried many, and many of them were not solved or were not ring disconnection. So we're just giving us standard chemistry, protection, deprotection. Okay, so we thought, okay, maybe we need to do a bit of work, and at the end, Eva's PhD has become training a model that can work for heterocyclic compounds. And that is easy to understand if we think about those systems are usually trained in the USP database. We can see a lot of cross-coupling chemistry there, amide bond formation, but actually very little heterocyclic ring formation. Okay. So with that, we started to train the model, and again, data accessibility is a challenge in this area. And even when you have the standard models, we're required to do our own cleanup and our own retraining of a baseline model, even though that has been reported before. But because the data is more difficult to access, we did that. And we train our own transformer model using this base general database. Okay, 1 million reactions coming from a wide range of chemistry. But if we think about, and we collected later also a range of different reactions that are heterocyclic compounds, not of the order of magnitude of the USPTO database, but representing interesting chemistry around. And this representation just illustrates that heterocyclic ring formation is challenging because it's not one type of reaction. Heterocyclic can be formed by condensation, but also through many different pathways. So we need to learn and identify chemistry that is all over the place, but different to the one that we have seen in the USPTO database. These are just a few examples of the reactions that we collected, in many cases manually from literature, plus other automated search to identify ring close information. And with that, we decided to train a new model and exploring a way to do that using transfer learning approaches. Okay, the idea was to combine these two approaches there. Just because training this alone actually is very specific and actually is not as good as, say, training something with the new chemistry that we have here. So we decided to explore from different transfer learning approaches. Maybe the most well-known is that have been used, for example, for carbohydrate chemistry or the Heck reaction, is that you train your general data set, and in the few layers before finishing, you retrain the model a few steps more with the chemistry that you want to teach. So think about this is doing like an undergrad in chemistry, and then your master will be much more specialized. What we have seen in this case is that, as happened when we do the PhD, we forget the chemistry that we have learned in undergrad. So you have this problem also here. Another approach was to combine them and train them at the same time using, for example, a 9-to-1 ratio or different ratios for the system. This has the disadvantage that the training time takes much longer, okay? What we decided to try for our two new approaches, that was the mix fine-tuning. In that case, you fine-tune your model, you train at the same time two of them, but also you introduce the baseline model again. So in case the system is forgetting during training, you introduce that back again. My students usually suggest that this is like you are doing your PhD here, but actually maybe you are teaching a bit to the undergrad, so you still remember maybe an hour a week some of the chemistry that you used to think about. And then the ensemble decoding, that is something that has been used in language model, and you have two models being predicted, and then you combine their predictions and make a new one from there. And what I will be presented today is this one, because this one we have seen is the best model that we see is able to predict ring closing reactions, but also to predict other type of chemistry that is not ring closing related. We also did, just for comparison, train a model similar to the ring closing, but retraining everything from the beginning, introducing the new reactions that we have been added as well to have a more fair comparison. How do we evaluate the models? Okay, there are different metrics, and nothing is perfect yet. Often people will say, this is my reactant, this is my product, and this is the reaction that I want to test. If I am doing retrosynthesis, what I want to do is compare my test product and identify if any of the predictions correlate with my reactants. That is a fair comparison, but also that means that we are trying to compare, is my system memorizing the reactant or not? So what now many people do is you allow the model to predict many different options, up to n predictions, and then you can compare them to the reactant that you have. A second validation is that you do a round-trip accuracy. Is that prediction giving you the product that you want? So you make sure that the system can go around all the circle, okay? But even with those metrics, sometimes they are missing because valid predictions don't mean that the chemistry that we want to predict is there, or the relevant chemistry is being predicted. Or maybe the prediction is just far down, so do we use a top 1, top 3, top 5 accuracy? And that remains to be discussed. So a few results that we have obtained so far from this model. What we can see, in this case, it was a fine-tuned model. So the first, this is our baseline model without knowing any new heterocyclic, apart the ones that were in the USPTO. And we can see that actually our model, the fine-tune and the mixed fine-tune model, can improve accuracy. This is around 15%, 18% accuracy, which may seem small. Previous examples have shown that you can obtain up to 25% increase in accuracy, but that was been for a forward synthesis, not retrosynthesis, and not in this diverse chemistry. So just with this top 5 accuracy, not going further in the predictions, we can increase predictability. And when we think about the valid disconnection, it's interesting that the baseline allow to have quite a lot of valid disconnections. But in many cases, many of them are not ring closing. They are just protections, deprotections. So that is important, and sometimes it's a bit biased what we see in those plots. So from here, we can see that the fine-tune model is the best one. It's improving the accuracy that we want. But actually, when we go to other type of chemistry, and this is just one example that I was mentioning before, is we have a product, and our model can predict a click reaction, very common for heterocycling ring formation. And the baseline can predict something, viable steps, but actually it's just a simple N alkylation, so a protection of the N group. So that is important sometimes to differentiate what we are predicting and what we're considering valid or not. In this case, we're also predicting a condensation. That is one of the most popular ways of doing ring closing. And in this case, we're just doing a ring functional group interconversion. So again, not touching the ring itself. So we see that our model is predicting ballistic connection, and actually those are related to ring closings. That is what we want. What happens when we go to all reactions? So let's use this model to predict different type of chemistry, and we have different data sets that will account to different type of chemistry in the USP database. And what we see is fine-tuning, forget quite a lot of the chemistry. What I used to tell you, if you use a fine-tuned model, it's like going into a PhD, you forget the chemistry that you have learned before. With the mixed fine-tune, because as a student, you're teaching maybe every week, then you can remember that chemistry as well. And that for that reason, we have seen the mixed fine-tuning has been the best compromise between learning new heterocyclic reinformation and also being able to be used in a multi-step retrosynthesis step. When we compare things to the template-based models available in the literature, we see that actually our model also performs better. In particular, give us most of the predictions that are made are viable, meaning we get a viable SMILE representation coming from there. In some other cases here, we just see a breakdown of the model. And the round-trip accuracy actually is much higher than those template-based models. But what is interesting is that when we compare those template-based models, in many cases for heterocyclic reinformation, they are still very accurate, and they predict different syntheses, which is very interesting. And we have seen that as a good way to use both models, actually, because they seem to learn different areas of the chemical space. For example, in our case, our model failed, but the rule, this one, both models can fail. The rule-based model failed here, but our model is working fine. And in the other way here, the rule-based model is working, giving a disconnection while the multitask is not. In some other cases, both predict the same cycle. So I think that is a good way to enhance the use, to improve the chances of getting disconnection, is actually to use the different approaches. Template-based models have been seen as sometimes outdated, but they are still very relevant. And they are indeed picking up chemistry that with the language models we are not yet picking up. What happens if we go to novel type of chemistry. So we took chemistry coming from 2022. Those were a couple of around 40 papers with different type of chemistry that we manually curated, 1,500 different reactions in that case. And we analyzed how our model will predict the general chemistry, the ring chemistry, and recent chemistry. And in our case, the new chemistry, because there are many different ways to identify new compounds, is enabled to predict exactly the same route that has been reported in 2022, but actually, so that can be seen here, we failed to predict that, but actually we predict for 30% of them other different pathways. Not exactly the same that we have from the literature, but those that are viable and come way down in the predictions that we have. So what we have done now is to find an easy way, and that is all in GitHub, where you can have the model and hopefully introduce and fine-tune further your model with new chemistry that is coming, because every year there will be new chemistry that we can teach the model. And indeed, when we have that, the model learns and improves substantially in the recent chemistry without forgetting other aspects of the general chemistry. And these are just few examples that we are presenting here. And what has been more exciting, and just to conclude, is the work that we have been doing in multi-step retrosynthesis. Okay, this is where we want to move the model forward, and we have been using this search algorithm that has been out there to use this retrosynthesis. This is chemistry that the model didn't know, standard molecules that have been reported, very relevant in drug medicinal chemistry. So this has reported in 2023. And what we can see actually is our model, the fine-tuned model, reproduces the literature. The baseline model has failed completely in that system, didn't provide any solution at all. And interesting, we can see that our model predict cyclization and the different steps, very similar to the one that has been reported in the literature here. This is another system, a product targeting kinases, and again, has an heterocyclic compound. In our case, we also identify different disconnections, but actually our model, and not the baseline, can identify the pyrazole disconnection, which allow us to actually suggest cheaper starting materials compared to the ones used originally in the publication. And this is the area that we want to move really, because we want to target the model to obtain cheaper compounds, hopefully greener starting materials that we can identify to obtain these heterocyclic compounds, rather than going to large state functionalization in those that are already known. And just to summarize, I was very happy to present today the work that Eva has been leading in my group, that has been leading with how we use transfer learning together with the transformer architecture to predict new heterocyclic compounds. We did test different approaches for transfer learning, and the mixed fine-tune has been the best one, compromising the improved accuracy in heterocyclic compounds, but also keeping the chemistry that is well known to be able to do retrosynthesis prediction of different molecules, including multi-step retrosynthesis of known drug-like compounds. And hopefully data availability can be improved, and hopefully we can keep improving to discover new chemistry. And with that, I would just like to thank everyone for listening today. To Eva, thanks all the work that she has been doing in providing those new ideas to move the project forward, and funders and colleagues in Exantia, who has been a great fun to work with. Okay, many thanks.
Thank you, Fernanda, for reminding us that we live in the real world, and we have to really keep in mind how real the molecules that we are designing have to be. Any questions? Yes. So I don't think that they can hear you. So please. Yeah.
Have you thought at all about using quantum chemistry to help predict perhaps some of these more difficult steps?
Yeah, that is, we're going back to that step, because initially we thought, okay, we will do just the chemistry that we usually do, quantum mechanics, mechanistic analysis. We have automated that, but there were 3,000 compounds, so like, oh, impossible. But now that we have a few ones, we are able to explore, and actually not even do the pathways, sometimes just looking at and the properties, electronic properties of the system, we have been able to select some promising ones from there, which have been tested actually. Hopefully they will be able to synthesize those there. And but a later stage has been the process there.
And have you looked at these reactions in the presence of solvent? Just a simple dielectric model, which actually seemed to help when we looked at some of these reactions, because you can have essentially a partial charge on maybe on the bond that you're breaking, and you need the effect of a dielectric to actually get a proper idea of the value and even of the route. Because some of the ones done in the gas phase even won't result in a reaction or the right intermediate, because you're not considering the effect of the solvent even with a dielectric model.
Yeah, you're completely right. The system seems very simple, small molecules, but the complexity they have, instead of, for example, think about tautomers that can be different in different compounds. And that have been an aspect that we have been aiming to explore from a different way, using machine learning potentials to explore solvent in those reactions. But again, there are so many aspects that we have to consider, that we are going at the space that when we really identify the promising ones that we want to work with, do a very detailed mechanistic analysis on those. Yes, it was an excellent talk. Thank you. Thank you.
Thank you very much. I think that we will take more questions during the coffee break. And thank you, Fernanda, once again.